In this segment, we will look at how to use block ciphers to encrypt multiple messages using the same key. This comes up in practice, for example, in file systems where the same key is used to encrypt multiple files. It comes up in networking protocols where the same key is used to encrypt multiple packets. So let's see how to do it. The first thing we need to do is to define what does it mean for a cipher to be secure when the same key is used to encrypt multiple messages. When we use the key more than once, the result of that is that the adversary gets to see many ciphertexts encrypted using the same key. As a result, when we define security, we're going to allow the adversary to mount what's called a chosen plaintext attack. In other words, the adversary can obtain the encryption of arbitrary messages of his choice. So for example, if the adversary is interacting with Alice, the adversary can ask Alice to encrypt arbitrary messages of the adversary's choosing, and Alice will go ahead and encrypt those messages and give the adversary the resulting ciphertexts. You might wonder, why would Alice ever do this? How can this possibly happen in real life? But it turns out this is actually very common in real life, and in fact this modeling is quite a conservative modeling of real life. For example, the adversary might send Alice an email. When Alice receives the email, she writes it to her encrypted disk, thereby encrypting the adversary's email using her secret key. If later the adversary steals this disk, then he obtains the encryption of an email that he sent to Alice under Alice's secret key. So that's an example of a chosen plaintext attack where the adversary provided Alice with a message and she encrypted that message using her own key, and then later the attacker was able to obtain the resulting ciphertext. So that's the adversary's power, and then the adversary's goal is basically to break semantic security. So let's define this more precisely. As usual, we're going to define semantic security under a chosen plaintext attack using two experiments, experiment 0 and experiment 1, that are modeled as a game between a challenger and an adversary. When the game begins, the challenger is going to choose a random key k, and now the adversary basically gets to query the challenger. So the adversary begins by submitting a semantic security query, namely he submits two messages, M0 and M1. I added another index, but let me ignore that extra index for a while. So the adversary submits two messages, M0 and M1, that happen to be of the same length, and then the adversary receives the encryption of one of those messages, either of M0 or of M1. In experiment 0, he receives the encryption of M0. In experiment 1, he receives the encryption of M1. So far this would look familiar. This looks exactly like a standard semantic security game. However, in a chosen plaintext attack, the adversary can now repeat this query again. So now he can issue a query with two other chosen plaintext, again of the same length, and again he would receive the encryption of one of them. In experiment 0, he would receive the encryption of M0. In experiment 1, he would receive the encryption of M1. And the attacker can continue issuing queries like this. In fact, we'll say that he can issue up to Q queries of this type. Again, remember, every time he issues a pair of messages that happen to be of the same length, and every time he either gets the encryption of the left side or the right side. Again, in experiment 0, he will always get the encryption of the left message. In experiment 1, he will always get the encryption of the right message. And then the adversary's goal is basically to figure out whether he is in experiment 0 or in experiment 1. In other words, whether he was constantly receiving the encryption of the left message or the encryption of the right message. So in some sense, this is a standard semantic security game, just iterated over many queries that the attacker can issue adaptively one after the other. Now, the chosen plaintext attack is captured by the fact that if the attacker wants the encryption of a particular message M, what he could do is, for example, use query J for some J, where in this query J he'll set both the 0 message and the 1 message to be exactly the same message M. In other words, both the left message and the right message are the same, and both are set to the message M. In this case, what he will receive, since both messages are the same, he knows that he's going to receive the encryption of this message M that he was interested in. So this is exactly what we meant by a chosen plaintext attack, where the adversary can submit a message M and receive the encryption of that particular message M of his choice. So some of his queries might be of this chosen plaintext flavor, where the message on the left is equal to the message on the right, but some of the queries might be standard semantic security queries, where the two messages are distinct, and that actually gives him information on whether he's in experiment 0 or in experiment 1. Now, by now, you should be used to this definition where we say that the system is semantically secure under a chosen plaintext attack if for all efficient adversaries, they cannot distinguish experiment 0 from experiment 1. In other words, the probability that at the end they output B prime, which we're going to denote by the output of experiment B, this output will be the same whether they're in experiment 0 or experiment 1. So the attacker couldn't distinguish between always receiving encryptions of the left messages versus always receiving encryptions of the right messages. So in your mind, I'd like you to be thinking of an adversary that is able to mount a chosen plaintext attack, namely, be given the encryption of arbitrary messages of his choice, and his goal is to break semantic security for some other challenge ciphertexts. And as I said, this game models the real world where the attacker is able to fool Alice into encrypting for him messages of his choice, and then the attacker's goal is to somehow break some challenge ciphertext. So I claim that all the ciphers that we've seen up until now, namely deterministic counter mode or the one-time pad, are insecure under a chosen plaintext attack. More generally, suppose we have an encryption scheme that always outputs the same ciphertext for a particular message M. In other words, if I ask the encryption scheme to encrypt the message M once, and then I ask the encryption scheme to encrypt the message M again, if in both cases the encryption scheme outputs the same ciphertext, then that system cannot possibly be secure under a chosen plaintext attack. And both deterministic counter mode and the one-time pad were of that flavor. They always output the same ciphertext given the same message. And so let's see why that cannot be chosen plaintext secure. And the attack is actually fairly simple. What the attacker is going to do is he's going to output the same message twice. This just says that he really wants the encryption of M0. So here the attacker is given C0, which is the encryption of M0. So this was his chosen plaintext query, where he actually received the encryption of the message M0 of his choice. And now he's going to break semantic security. So what he does is he outputs two messages, M0 and M1 of the same length, and he's going to be given the encryption of MB. But lo and behold, we said that the encryption system always outputs the same ciphertext when it's encrypting the message M0. Therefore, if B is equal to 0, we know that C, this challenge ciphertext, is simply equal to C0 because it's the encryption of M0. However, if B is equal to 1, then we know that this challenge ciphertext is the encryption of M1, which is something other than C0. So all the attacker does is he just checks if C is equal to C0, he outputs 0. In other words, he outputs 1. So in this case, the attacker is able to perfectly guess this bit B, so he knows exactly whether he was given the encryption of M0 or the encryption of M1, and as a result, his advantage in winning this game is 1, meaning that the system cannot possibly be CPA secure. 1 is not a negligible number. So this shows that deterministic encryption schemes cannot possibly be CPA secure, but you might wonder, well, what does this mean in practice? Well, in practice, this means, again, that every message is always encrypted to the same ciphertext. What this means is if you're encrypting files on disk and you happen to be encrypting two files that happen to be the same, they'll result in the same ciphertext, and then the attacker, by looking at the encrypted disk, will learn that these two files actually contain the same content. The attacker might not learn what the content is, but he will learn that those two encrypted files are an encryption of the same content, and he shouldn't be able to learn that. Similarly, if you send two encrypted packets on the network that happen to be the same, the attacker will not learn the content of those packets, but he will learn that those two packets actually contain the same information. Think, for example, of an encrypted voice conversation. Every time there's quiet on the line, the system will be sending encryptions of 0. But since encryptions of 0 are always mapped to the same ciphertext, an attacker looking at the network will be able to identify exactly the points in the conversation where there is quiet, because he will always see those exact same ciphertexts every time. So these are examples where deterministic encryption cannot possibly be secure. And as I say, formally we say that deterministic encryption cannot be semantically secure under a chosen plaintext attack. So what do we do? Well, the lesson here is if the secret key is going to be used to encrypt multiple messages, it had better be the case that given the same plaintext to encrypt twice, the encryption algorithm must produce different ciphertexts. And so there are two ways to do that. The first method is what's called randomized encryption. Here the encryption algorithm itself is going to choose some random string during the encryption process, and it's going to encrypt the message M using that random string. So what this means is that a particular message M0, for example, isn't just going to be mapped to one ciphertext, but it's going to be mapped to a whole ball of ciphertexts, where on every encryption, basically we output one point in this ball. So every time we encrypt, the encryption algorithm chooses a random string, and that random string leads to one point in this ball. Of course, the decryption algorithm, when it takes any point in this ball, will always map the result to M0. Similarly, the ciphertext M1 will be mapped to a ball, and every time we encrypt M1, we basically output one point in this ball, and these balls have to be disjoint so that the encryption algorithm, when it obtains a point in the ball corresponding to M1, will always output the message M1. In this way, since the encryption algorithm uses randomness, if we encrypt the same message twice, with high probability we'll get different ciphertexts. Unfortunately, this means that the ciphertext necessarily has to be longer than the plaintext, because somehow the randomness that was used to generate the ciphertext is now encoded somehow in the ciphertext. So the ciphertext takes more space. And roughly speaking, the ciphertext size is going to be larger than the plaintext by basically the number of random bits that were used during encryption. So if the plaintexts are very big, if the plaintexts are gigabytes long, the number of random bits is going to be on the order of 128, so maybe this extra space doesn't really matter. But if the plaintexts are very short, maybe they themselves are 128 bits, then adding an extra 128 bits to every ciphertext is going to double the total ciphertext size, and that could be quite expensive. So as I say, randomized encryption is a fine solution, but in some cases it actually introduces quite a bit of cost. So let's look at a simple example. So imagine we have a pseudo-random function that takes inputs in a certain space R, which is going to be called a nonce space, and it outputs in the message space. And now let's define the following randomized encryption scheme. When we want to encrypt a message M, what the encryption algorithm is going to do is first it's going to generate a random R in this nonce space R, and then it's going to output a ciphertext that consists of two components. The first component is going to be this value R, and the second component is going to be an evaluation of the pseudo-random function at the point R, XORed with the message M. And my question to you is this encryption system semantically secure under a chosen plaintext attack? So the correct answer is yes, but only if the nonce space R is large enough so that little r never repeats with very, very high probability. And let's quickly argue why that's true. So first of all, because f is a secure pseudo-random function, we might as well replace it with a truly random function. In other words, this is indistinguishable from the case where we encrypt the message M using a truly random function little f evaluated at the point R and then XORed with M. But since this little r never repeats, every ciphertext uses a different little r, what this means is that the values of f of r are random, uniform, independent strings every time. So every time we encrypt a message, we encrypt it essentially using a new uniform random one-time pad. And since XORing a uniform string with any string simply generates a new uniform string, the resulting ciphertext is distributed as simply two random uniform strings. I'll call them R and R prime. And so both in experiment 0 and in experiment 1, all the attacker gets to see are truly uniform random strings R, R prime. And since in both experiments the attacker is seeing the same distribution, he cannot distinguish the two distributions. And so since security holds completely when we're using a truly random function, it's also going to hold when we're using a pseudo-random function. Okay, so this is a nice example of how we use the fact that a pseudo-random function behaves like a random function to argue security of this particular encryption scheme. Okay, so now we have a nice example of randomized encryption. The other approach to building chosen plaintext secure encryption schemes is what's called nonce-based encryption. Now, in a nonce-based encryption system, the encryption algorithm actually takes 3 inputs rather than 2. As usual, it takes the key and the message, but it also takes an additional input called a nonce. And similarly, the decryption algorithm also takes the nonce as input and then produces the resulting decrypted plaintext. So what is this nonce value n? This nonce is a public value. It does not need to be hidden from the adversary, but the only requirement is that the pair key comma nonce is only used to encrypt a single message. In other words, this pair k comma n must change from message to message. Then there are 2 ways to change it. One way to change it is by choosing a new random key for every message, And the other way is to keep using the same key all the time, but then we must choose a new nonce for every message. And as I said, I want to emphasize again, this nonce need not be secret and it need not be random. The only requirement is the nonce is unique. And in fact, we're going to use this term throughout the course. A nonce for us means a unique value that doesn't repeat. It does not have to be random. So let's look at some examples of choosing a nonce. Well, the simplest option is simply to make the nonce be a counter. So for example, in networking protocol, you can imagine the nonce being a packet counter that's incremented every time a packet is sent by the sender or received by the receiver. This means that the encryptor has to keep state from message to message, namely it has to keep this counter around and increment it after every message is transmitted. Interestingly, if the decryptor actually has the same state, then there's no need to include the nonce in the ciphertext since the nonce is implicit. Let's look at an example. The HTTPS protocol is run over a reliable transport mechanism, which means that packets sent by the sender are assumed to be received in order at the recipient. So if the sender sends packet 5 and then packet 6, the recipient will receive packet number 5 and then packet number 6 in that order. This means that if the sender maintains a packet counter, the recipient can also maintain a packet counter, and the two counters basically increment in sync. In this case, there's no reason to include the nonce in the packets because the nonce is implicit between the two sides. However, in other protocols, for example in IPsec, IPsec is a protocol designed to encrypt the IP layer. The IP layer does not guarantee in-order delivery, and so the sender might send packet number 5 and then packet number 6, but those will be received in reverse order at the recipient. In this case, it's still fine to use a packet counter as a nonce, but now the nonce has to be included in the packet so that the recipient knows which nonce to use to decrypt the received packet. So as I say, nonce-based encryption is a very efficient way to achieve CPA security, and in particular if the nonce is implicit, it doesn't even increase the ciphertext length. Of course, another method to generate a unique nonce is simply to pick the nonce at random, assuming the nonce space is sufficiently large so that with high probability the nonces will never repeat for the life of the key. Now in this case, nonce-based encryption simply reduces to randomized encryption. However, the benefit here is that the sender does not need to maintain any state from message to message. So this is very useful, for example, if encryption happens to take place on multiple devices. For example, I might have both a laptop and a smartphone. They might both use the same key, but in this case, if I required stateful encryption, then my laptop and the smartphone would have to coordinate to make sure that they never reuse the same nonce. Whereas if both of them simply pick nonces at random, they don't need to coordinate because with very high probability, they'll simply never choose the same nonce. Again, assuming the nonce space is big enough. So there are some cases where stateless encryption is quite important, in particular where the same key is used by multiple machines. So I want to define more precisely what security means for nonce-based encryption, and in particular I want to emphasize that the system must remain secure when the nonces are chosen by the adversary. The reason it's important to allow the adversary to choose the nonces is because the adversary can choose which ciphertext it wants to attack. So imagine the nonce happens to be a counter, and it so happens that when the counter hits the value 15, maybe at that point it's easy for the adversary to break semantic security. So the adversary will wait until the 15th packet is sent, and only then he will ask to break semantic security. So when we talk about nonce-based encryption, we generally allow the adversary to choose the nonce, and the system should remain secure even under those settings. So let's define the CPA game in this case. And it's actually very similar to the game before. Basically, the attacker gets to submit pairs of messages, MI0 and MI1. Obviously, they both have to be of the same length. And he gets to supply the nonce. And in response, the adversary is given the encryption of either MI0 or MI1, but using the nonce that the adversary chose. And of course, as usual, the adversary's goal is to tell whether he was given the encryption of the left plaintext or the right plaintext. And as before, the adversary gets to iterate these queries, and he can issue as many queries as he wants. We usually let Q denote the number of queries that the adversary issues. Now, the only restriction, of course, which is crucial, is that although the adversary gets to choose the nonces, he's restricted to choosing distinct nonces. The reason we force him to choose distinct nonces is because that's the requirement in practice. Even if the adversary fools Alice into encrypting multiple messages for him, Alice will never use the same nonce again. As a result, the adversary will never see messages encrypted using the same nonce, and therefore, even in the game, we require that all the nonces be distinct. And then, as usual, we say that the system is a nonce-based encryption system that's semantically secure under a chosen plaintext attack if the adversary cannot distinguish experiment 0, where he's given encryptions of the left messages, from experiment 1, where he's given encryption of the right messages. So let's look at an example of a nonce-based encryption system. As before, we have a secure PRF that takes inputs in the nonce space R and outputs strings in the message space M. Now, when a new key is chosen, we're going to reset our counter R to be 0. And now when we encrypt a particular message M, what we'll do is we'll increment our counter R and then encrypt the message M using the pseudo-random function applied to this value R. And as before, the ciphertext is going to contain two components, the current value of the counter and then the one-time pad encryption of the message M. And so my question to you is whether this is a secure, nonce-based encryption system. So the answer, as before, is yes, but only if the nonce space is large enough, so as we increment the counter R, it will never cycle back to 0, so that the nonces will always be unique. We argue security the same way as before. Because the PRF is secure, we know that this encryption system is indistinguishable from using a truly random function. In other words, if we apply a truly random function to the counter and XOR the results with the plaintext M. But now, since the nonce R never repeats, every time we compute this f of R, we get a truly random, uniform, and independent string, so that we're actually encrypting every message using the one-time pad. And as a result, all the adversary gets to see in both experiments are basically just a pair of random strings. So both in experiment 0 and in experiment 1, the adversary gets to see exactly the same distribution, namely the responses to all his chosen plaintext queries are just pairs of strings that are just uniformly distributed, and this is basically the same in experiment 0 and experiment 1, and therefore the attacker cannot distinguish the two experiments. And since he cannot win the semantic security game with a truly random function, he also cannot win the semantic security game with the secure PRF. And therefore the scheme is secure. So now we understand what it means for a symmetric system to be secure when the key is used to encrypt multiple messages. The requirement is that it be secure under a chosen plaintext attack. And we said that basically the only way to be secure under a chosen plaintext attack is either to use randomized encryption or to use nonce-based encryption where the nonce never repeats. And then in the next two segments, we're going to build two classic encryption systems that are secure when the key is used multiple times.